can't wait to hear your presentation. So, without further ado, I'll introduce you to Ricardo. Well, anyway, needless to do that, because it's easy, isn't it, Ricardo? Everybody knows who you are, what you stand for, and I'll be happy to give you the floor.
FSS-congres, want ja, het zou...
Okay, it won't have escaped you that the past few years as Firefighting Academy, along with Firefighting Netherlands, we conducted quite a bit of research. In the autumn alone, we issued 5 reports, and there's still a number of researches in the pipeline. So, on the program, it says that we're going to talk to you about our response, but when we set up the program, we thought that we were done with this subject. But, you know, that's how things go with your research when you analyze your results. So there's still a number of question marks, and we haven't been able to solve all these questions. Yesterday, we talked to Robin from UL about a number of these results, and it turns out that we are not the only ones facing issues that we really hadn't expected. So I am going to reveal part of the subject, but I'm not going to go through all the details and present final conclusions because we can't do that. But it might be interesting to take you along in a number of other things that we found out over this past year between the last FSS conference and this one. And what I'll also do is explain again why it is that we're doing this, because for lots of you, it'll be cut and dried. But there are lots of new people from abroad here in the room. I see people from Portugal, from Belgium, and people from Zeeland, the province in the south of the Netherlands. Zeeland, yeah. I said that to them yesterday. You don't very often get people from Zeeland. Anyway, they're not all in this room. They're in the room next door. But it's great for us to be able to talk to them. But what you don't know is that there are people in Minsk. There are 20 students in Minsk, and if you've that are following us. So I promised that I would wave. Hi, Minsk. So especially for those people, I think it might be a good idea to explain that this study that we're carrying out in the Fire Service Academy is not a hobby of the professor. It's something that fits within a broader context. And we have a specific purpose for doing this. So let me go back to why we need this research. And the main reason, and I think that is first on the list, is firefighter safety of our colleagues when we respond. And the fire department has promised to do everything in its power to avoid any more casualties. And we know, and we picked up on all sorts of signals that, and we heard that yesterday, that fires have changed. Fires nowadays will be ventilation controlled as soon as we get there, and that there are extraordinary dangers involved in that. We all know that, and we heard that yesterday. That's an important driving force behind research. And what we also see is that very often we think we know things, but it's not always what we think it is, or we don't always know everything, and or everything we were supposed to know. So research is very important for that. And the management, the fire department in the Netherlands, has acknowledged that. We have 2010 vision, the vision for tomorrow, and the most important issues are the firefighting doctrine and conducting more research. The idea behind that is that slowly but surely we're facing more and more problems that can no longer be solved with tiny little solutions, but that we really need to innovate as a fire department. Innovation without knowledge is impossible as far as I'm concerned. So you really need know-how in order to be able to innovate. The fire department doctrine is this bow, really. The bow shows that we have a probability and an effect side, and the parts of this bow is exactly what we want to innovate. So we need to move towards the front. We're not going to talk about that here today, but all this will lead to more information in order to advise civilians as to what they should do. Anyway, that's something that we're going to talk about this afternoon. Margrethe Kolen and Karen Groenemeter are going to talk to us about the smoke detectors. But we're at the back, really. What could you do in order to innovate suppression rather? And what is the knowledge that you need? And fire investigation is very important, and also know-how. Innovation of suppression is very important. Why? First of all, those fires have changed, and we need to adjust our procedures to new types of fires. And yesterday, we listened to Sean de Grain's presentation, and we'll be facing so many more challenges. And we'll have to look into all these challenges, see what that means for our suppressive response, what kind of techniques and tactics can we develop in order to pull this off. So it's all about firefighter safety, but also improving efficiency. But in other respects, we have to understand that there are limits to what we can do, and where are those limits? If we look at the iron batteries that Sean de Grain showed us yesterday, well, if you can't include it in the building code as a fire department, we have to say, okay, there are just limits to what we can deal with. And we also have to make that very clear. And one of the main things that we've developed in the context of innovation is this model of quadrants, and it has also been translated into Belgium, into Flemish, French, English, and those people who listen to Tony Hunter, they know that this quadrant model has been adopted in the UK, and there are more and more firefighting departments in the UK that are using this, and also to develop the offensive exterior attack, and they're implementing this, and we are researching this mainly. 4 quadrants, 2 of which are reasonably new, of which you could say, well, the offensive exterior attack, when we first talked about it, firefighters said, well, that's great, but how are we really going to go about it? That's what we're going to focus on in our study. I'm going to tell you more about that, but the other quadrants also require attention. Defensive outside attacks, something we've been doing for years, but how do we do that? How does it work? Can we improve efficiency? Can we do it with less water, for instance? All this polluted water that is wasted, all these social problems, and we're trying to find solutions for those issues in our study. Research, of course, if you want to innovate, your doctrine is innovation. Innovation is your main target, so for that you need know-how about fire dynamics, causes of fires, and effects of techniques that you are going to deploy. And you can't only do that with experiments that I'm going to talk to you about. We know that by now. Doing these experiments, by the way, is a gigantic learning process. I'll tell you more about that later on, how we started and how we've developed and where we stand now. I mean, it's an enormous process of learning, changing, improving, etc. But something else that we found out, you see, these practical experiments are experiments that you do in a particular situation. And of course, what we want to do is that we can tell our firefighters in the field, okay, we've done an experiment, and this is what it means for you guys. Clear action perspective. Scientists say, well, yes, no, and that can only apply for the situation that we tested. And in order to broaden this, really, broaden our perspective, you have to link up all sorts of research methods. And so now we have know-how about fire safety engineering. What you see is that models, and Daniel Joyeux yesterday had 6 sheets with questions that had yet to be answered in order to improve fire safety engineering. For that, you need practical experiments. The combinations between these experiments is extremely important. The other way around, if we're going to do experiments, it might be very nice to know more or less what the expected outcome will be, or how to best structure such an experiment. And this link is very important, FSE and experiments. So once we've done an experiment, the colleagues could say, well, yeah, well, we never see that in practice. That does happen. And 90% of the fires, we still extinguish the fires with 45 or with a bucket of water. What are you talking about? So that is why it is so important to investigate practical fires and combine that with the experiments that you're carrying out in order to get some idea as to whether the experiments that you're carrying out have any relation to practical examples. Well, in Zutphen, we had 6 scenarios. And we thought, well, there'll also be conflagration, I'm sure. And there were 2 colleagues out there, and none of the fires really fully developed. We were quite surprised about it. And I talked to colleagues, and I said, how come? And the colleague said, well, we see this very often. Strange thing is that I never hear anything about this, because apparently these conflagrations are something that we have in mind, but the ventilation-controlled fires was something that we never discuss. So we are gathering case studies on that. So a combination of all that will lead to know-how. These practical experiments, we don't do them in a laboratory. We want to involve as many people across the country as possible, and we were quite successful because you can see that here in all these experiments we had hundreds of firefighters involved, and that gives excellent interaction. We get practical experience from the field and the best possible link between craftsmanship and academia. There's exchange of ideas, of know-how. I'm extremely proud of the fact that we succeeded with people from the field to actually carry out these studies. All these experiments are carried out by firefighters who know how everything works and who actually have a contribution to make in that respect. As I said, fire investigation is extremely important. I'm very, very proud of the fact that here in the Netherlands nowadays we have excellent fire investigation teams, high quality, that are able to give us high quality data. And as an academy, we zoom into certain subjects and we gather information that we can link up to each other. And what we do in ZETFA, I mean, if it does happen so frequently, these ventilation controlled fires, we want to know what the outcome is. So we are asking colleagues, and we're asking you actively, so if you ever experience such a fire that is interesting, that you should share that information with us, because that way we can connect the fire in practice to these experiments, and that way we can really make headway in innovation. So that's the entree. You're still awake? Who didn't know about this? Oh, everybody knew about it. Okay, so everybody already knew about this. Well, that's fine. I hope that it was interesting nonetheless. Possibly abroad, people might think it's interesting to know this. Anyway, you will recognize this. All the experiments are here in the schedule. The blue ones will be discussed. I can't discuss everything here today, but there are a number of experiments that I'm sure you'll be familiar with. But you will recognize the quadrant model. And you see that we are active in each and every quadrant of the model. We carry out experiments in order to increase our knowledge, see how we can improve safety. And sometimes we find out that things that we thought were okay are not so okay. Before I proceed to offensive exterior attack, last year, I said that we want to do something about defensive exterior attack, but that is really a problem for us. I mean, how can you make sure that there's no flash over? We do that every day, or put a water screen as we were taught. Well, that's not how we were taught, but anyway, because it doesn't say so in the manual. But that is how we were taught to do it in practice. So that's what we do. So we've been thinking how to go about this, because you want to repeat an experiment a number of times. Well, we don't have premises with 20 buildings that you can all set fire to and see what happens. No, we had to set up a structure. Now that is not as easy as you may think. And one of the questions here, and some physicians, physical experts say this, if there's radiation in the fire, radiation permeates everything. Why doesn't it permeate water? That's the first question we asked. There was a student, Alan, and Alan developed a structure and did some initial experiments. It's not entirely what we want. It was sort of initial research. And the first thing she looked into was the absorption of radiation by water. And this is a picture of the structure. You see that we've done this with firefighters, actual firefighters. I didn't know that, but water is kind of a strange liquid, strange substance in terms of absorption of electromagnetic radiation coming from flames, because it turns out that by coincidence, radiation from flames of about 600 degrees in wavelength are between 3 and 10 micrometers, and water, here's water, plays a part in the absorption of that radiation. That explains why water works very well to stop radiation. That may be a bit of news for you, news tidbit. There you go, you didn't know about this. But you could find it in literature, but anyway, it was new for me. Because my whole career, for 23 years, I've been wondering, how come this works? And does it work? So perhaps we may think that it works. Or perhaps the fire would never have flashed over. Anyway, So we did all these experiments, and here we have a metal sheet, and the metal sheet with the radiation testing equipment. And the trick was that we needed a radiation source that is constant. You can't just make a big fire, because that way the flames go in all directions and you don't have a constant radiation. And we were able to do that by setting up a container looking like this, with all sorts of pallets. It was open on one side, and there's a steel wall on one side. It was very exciting because we didn't know how much radiation there would be, but it went reasonably well. And this is the structure, the layout. Here you see the container, here you see the sheet, and here we ignite the fire. Radiation goes to the sheet. 1, 2, 3 times without a water screen. And once we also had water drip along the sheet. So this is the graph. This is a graph without anything in between. This is radiation that we measured on the wall side between 7 and 9, which is considerable radiation temperature here. And here with water screen, you see the radiation is being reduced quite considerably. And this one is with the water screen and a water layer on the metal facade. And you see that the radiation is the same, but that's correct because we were measuring the heat radiation next to the wall. Temperature, quite interesting. You see that these experiments can be reproduced. Temperature between 600 and 700 degrees without anything in between. You see the temperature of the sheet increases to 200 degrees, water screen 150, and if you have water layer on the metal facade and you put a water screen, it's only 40 degrees, which means that a water screen does absorb water. It's about does absorb radiation, about 50%, because it's not entirely closed. It doesn't absorb all the radiation, but it's better to make sure that there's a layer of water on the adjoining wall. So it does work. The screen does work, but it's even better if it sprays water along the wall so that you have this thin layer of water on the wall. Okay, that's interesting, isn't it? Okay. Okay, we're going to work on this more. We want to expand our knowledge. But in any case, what we can say is that this layout worked rather well and that we saw a difference between these different ways of working. Something else that I don't want to deprive you of is that this past year, we also talked about smoke gas cooling with foam. You may remember the upheaval when we issued the first report. We had shots in the smoke, but there was no cooling of smoke gases, and the manufacturer said you didn't do this properly because you'd got to do this differently. We have a different method to accomplish this. You have to apply this to the ceiling and the walls. A number of regions did that, so we said, okay, let's check and see if that is working. And what is the case? It works better than the method that we first applied. So this is the graph, the way we did it the first time. Here you see that hardly anything happens in terms of cooling. And this is if you follow the half-moon technique and you spray it along the walls and the ceiling. That's how it works. Works rather well. What you do see is that you need a bit more water. And low pressure, by the way, in these situations does also work very well. You see that here, this curve here, and you see that here in the red line. Low pressure works very well. And why is this so interesting? Because this has led to the following, what you see here. These cycles, you see this particularly in high pressure, low pressure less so, particularly in the beginning. And what you also see is that this is the thermocouple that is halfway the container. Halfway the container, first, you don't see very much happening with the fire gas cooling, but only when you reach this point where you see the temperature, here you see the temperature drop. And this has led us to the following. You'll see some more pictures that fire gas cooling does work, but you see the temperature drops, increases, actually to here until the same temperature. You see this in higher temperature. So that means something about the restrictions and limitations of fire gas cooling. Next year, we want to zoom into that and find out more about it, because we want to know a bit more about the restrictions and limitations of fire gas cooling. The offensive exterior attack. This is the picture. Is he still here? Is he here? Yeah, Johan is over here. We can always see him here, because this is a picture of the fire in Harlingen, in the north of the country. This is the closed box. We see the smoke coming out, and you're thinking, oh God, what should I do? You're there in front of the door, and you're wondering whether it's dangerous, not dangerous. And what we did was open the door, and then we looked around. We opened all the doors. And nowadays we know that we shouldn't do that, because if we open doors, the fire will just exacerbate. So the question is, what should you have done? Offensive exterior attack. How to do that, and will that work in all circumstances? The question is, what do we do with ventilation-controlled fires, particularly in these industrial warehouses? The idea of offensive exterior attack is that you arrive with your fire engine, you get a piece of equipment, and then you attack from outside. Either you are capable of extinguishing the fire, or creating a situation that is safe to go inside and to extinguish the fire. And what we also thought was that for people who were inside, the survival rate could increase. And I'm going to talk about it later on. The idea was the temperature would decrease, and as a consequence, survival rates would increase. Now we know that temperature is not the only element here, but we'll be discussing that later on when I discuss the results. But also, just imagine that you're able to create a situation that's safe enough to enter the building to extinguish the fire. How much time do you have? Because it would be a bit of a pity if, first of all, you get the temperature to go down to 150 degrees. You go inside, and then it all fires up again. So in the measurements, we looked at what happens if, after such an offensive exterior attack, you open the door, and how much time it takes for the fire to exacerbate. So what we looked at are a number of techniques that already exist. This spray distribution nozzle, very well known in the south of the country. The cold cutter, a new one. Fog nails, particularly a technique used in Utrecht for thatched roofs. And the foam, lots of people have the foam and ventilation to a certain extent, to a limited extent, because we find it scary. We don't really understand it very well. So we are very excited because we know that UL is going to do these experiments. So we said, okay, let's just wait and see what they find out. We may not have to do these experiments and just learn from what they've done in the US. Buildings now, 2 buildings or 3 buildings really. A big warehouse, we used that one in OB1 and OB5, and OB2, 3, and 4, we used a container building with interconnected containers in different configurations. OB1 and 5, OB1, you see that this was one of the first studies we did. We only had thermocoupling at the time, so we only measured the temperature, and we put a stack of pallets in the building, and the possibility was if you could make a hole in the door, you could go in, and then with a jet you could hit the source of the fire. So what if you can't hit the fire burden, the fire load? In OB5 we did that. If we make a fire that you cannot hit from the door opening directly, can you then achieve the same result? In both cases, a reasonably large fire. Couldn't have been much bigger, because that way the building would burn down. In OB5 we had lots of problems to use the building 20 times. The first time all the sheets fell down. Anyway, I'm not going to bore you with all these experimental problems, but I can assure you that it's not as simple as it may seem. And Rijk and Karin had a bit of trouble making sure everything went well. OB1 was a fire load that could be reached. OB5 was after the fire in Zutphen, and Zutphen, we did a lot of measurements about radiation, carbon monoxide. OB5 apart from temperature, we were able to measure all sorts of other things. And now the container building, we started OB2 and 3, and we had 4 connected spaces. And the question was, what if the fire is in a space that is further away? So I'm at the front door, and the fire is right at the back. And I enter through the front door, and I want to start extinguishing. What are you going to do with the fire that is farther away? And can I make sure that all these spaces are safe, not only the first space where I enter, all the other ones as well? So at the time, we only had the thermocouples, and we put victims in there to find what happens at this height, at the temperature. And so we took a very scientific approach. The idea was we've got to be very scientific about it because otherwise we can't really prove things. And we said, okay, at the front door, once you've arrived there, you can respond for 30 seconds and then take a 30-second break and then start again. That way you can compare the techniques. Ultimately, that leads to outcomes, and the firefighters in the field say, well, that's rubbish. We're not going to do that, and we're not going to wait for 30 seconds. We're just going to go on and on. In other words, we said, okay, in OB4, that's precisely what we're going to do. We're going to see if you respond as long as you think is necessary with a maximum of 10 minutes, because otherwise you can just go on and on. So we said a maximum of 10 minutes, you can attack. And then at OB4, at lower height, we had all these parameters because in the meantime, we had purchased all these measurement equipment. So not as many as we wanted to have. We're not the only ones with the problem purchasing measuring equipment. It's very expensive, and I'm sure we'll be hearing more about that. You'd like to measure more, but there are some restrictions to what you can do. If you look at this big warehouse, we had a fire load of about 15,000 megatube. We don't know exactly that is in terms of HRR, heat release rate. We believe somewhere between 5 and 8. And in these fires in this container building, 2 and 4. So it's just like a living room fire. It can be compared to that. We don't know exactly.
It all depends on ventilation, other factors, so it's difficult to measure. Now, OB1, we saw that last year, that large shed, and the conclusion was that the techniques from outside work fairly well, the cold cutter and the fog nail, but we really wanted to hit that fire. The temperature in the shed dropped very quickly below 150 degrees, but once you're inside, things slow down a lot, so perhaps it's better to fight it from outside, but that's if you can reach the fire hearth inside, wherever it is. So at OB2 and 3, we used a building of 4 rooms, and that report is done. It will be published in Dutch soon. We want to have it translated into English. We want to share our knowledge with our counterparts outside, so we'll be translating it into English. And we have a map here. The fire truck rode up, and the fire is there. There are 2 victims, one there and one there, and here's where we deploy. We measured the temperatures at a height of 6 feet and at the living level. And after that, we shifted to a different space, but we weren't able to quantify the results there. It was basically estimation. Now, if you operate in space 1, what happens in the other spaces? If you look at the temperature with each of the deployment techniques in room 1, we see that basically only the cold cutter and repressive ventilation achieve continuous drops in temperature and get that temperature below 150 degrees. The same holds true for some of the other rooms. I'll show you that on the next sheet. You see that the spray nozzle is not very effective in the double foam fog nails with high pressure and low pressure. Well, they do have an impact, but nowhere near as much as the cold cutter and ventilation achieve. Again, you see a typical process, so you wonder whether if you enter the room, can you assume that cooling the fire gas will be limited in duration and scope. And that's true, because as long as you don't throw water on the fire continues to exude hot gases. So throwing water on fire is the best way of cooling smoke. Now, if you examine all the rooms, this might seem a little bit complex, but we've got 4 rooms here, and the temperatures In room 1, 150 degrees, but the fire was over here in room 4, so the temperature dropped a bit into room 1. And you see that in room 4, none of the techniques would make a substantial impact. And that's unfortunate because we thought that external deployment would make it possible to extinguish the fire from outside. And in room 3, there was hardly any effect either. In fact, some techniques led the temperature to rise. We still don't understand exactly why that is. Some people say it's because of the cold block and the exit of hot gases is affected by the quantity of steam that's in the ambience. What does work is ventilation, and in room 2, that's the room directly behind room 1, you see that the cold cutter and ventilation are effective, but the other are minimally effective. And you see that in room 1, all techniques are reasonably effective, whether you're talking about the spray nozzle or the fog nails. They do get the temperature below 150 degrees, but the temperature was not very high to begin with there. And from here, we said, my goodness, there is a problem, because that means it makes a great difference where you deploy. If you try to deploy a fireman from outside, but that wasn't really the idea. Well, that's why you're conducting the research, and that was the initial conclusion. In all 4 rooms, we said, okay, let's take a closer look, because it almost seems as if you need to deploy in the area of the fire. So spraying water on fire is the best way to cool. How would the different techniques work, and what would happen if you were in the area adjacent to the fire? So we tried using all 4 techniques there, and we immediately adjusted that for the 30-second on, 30-second off method. We said just operate as usual, but do not exceed 10 minutes. This is what it looked like. Here's the map. This was the fire room. So we sealed the other containers, and here's the adjacent room, and we deployed here and there. So we conducted 2 types of experiments. First, we conducted an experiment where we deployed immediately in the fire room from outside, and then we conducted an experiment with all the techniques. Over here, there were 3 victims in all the different rooms, and we had the necessary measurement equipment to see what the survival rate would be. And we conducted each experiment twice. And then you get there, because the question is, what are the survival options? How do you measure it? Previously, it was easy. If the temperature exceeded 120 degrees, it would be difficult to survive. But now some additional parameters came into play. And it's almost a PhD study to get those parameters right. There's an awful lot of literature about those parameters, but most of it's dated. And we consulted some professors for Zutphen who didn't agree either. And at this point in time, if I listen to this from our foreign friends, these seem to be the most plausible parameters. Temperature, 120 degrees centigrade. The radiation, 6 kilowatt per square meter. Carbon monoxide, 8,000 ppm. Carbon dioxide. We measured them all. Here are some graphs. What we hadn't done the first time was baseline measurements, because the question afterwards was, what would have happened if you hadn't done anything? Would the same thing have happened? So now we did that. Both with OB4 and OB5, we conducted a baseline measurement. We left the fire and closed the doors and saw what would happen if we didn't do. And this is if you deploy in the fire room. You see that the temperature remains constant. So basically, the fire doesn't change very much about the temperature. Next, if you look at the extent of the cooling, you see the baseline measurement here. So this is what would happen if you do nothing, and this is what happens if you deploy. And you see that all deployment techniques that we applied do cause the temperature to drop below 150 degrees in the fire gas layer pretty quickly. And it doesn't matter how you do it, as long as you do it intelligently. They didn't just spray at random. They sprayed the way they learned to spray inside, and then you get the temperature below 150 degrees within 1 minute. That was good news. So the hypothesis that deployment in the fire room always works is good. Now, if you look at time to achieve knockdown, are you able to extinguish the fire? You'll see that within 4 to 14 seconds, all those fires are no longer in full blaze. They're still smoldering, and then the question is, can we enter to extinguish everything? How much time do we have? Once you open the door, that's what we did. We opened the door to see what happened. And you see that with the cold cutter, the spray nozzle, and the fog nail, you see that it reignites within a couple of minutes, within 3 minutes, and then the temperature really surges. So that means that once you enter, you have a couple of minutes to extinguish the fire. And if the room isn't large, then you'll probably succeed. With low pressure and air pressure foam, we didn't see that reignition, so we achieved continuous knockdown there, so that the fire had really been knocked out, and we were able to finish extinguishing it. This was deployment in the fire room. If you look at the survival rates, we saw something remarkable, because that revealed that the temperature was not the main issue. This is baseline. If you look at the baseline measurement, you see that in addition to temperature, radiation and carbon monoxide seriously affect survival rates. So if we did nothing, there would be 3 things that would kill the victim. He would really heat up. And he would also inhale a lot of carbon monoxide above the 8,000 ppm rate. And if you do deploy, then you see that the temperature is not a problem. We do improve the temperature, at least that's what we thought. That's why we thought that deploying a fireman from outside would work. But you don't really change the other parameters a lot. So you see red somewhere. And if you see a half red person, then once it worked and the other time it didn't work. So that's not rock solid proof for us. But you do see that the other parameters are so important for survival rates, and that in those parameters, you're more likely to make the situation worse through deploying than that you improve the situation. That's one area where the jury is still at. We see with all experiments, both in OB4 and at OB5, that the moment you deploy with water or air pressure foam or whatever, radiation rises. Who was present at the OB5 experiments? Is there anybody here in the room who was present? A couple of you? Okay, at OB5, we invited some people to watch the measurement equipment, and we were all amazed at how, when we deployed, the radiation suddenly soared. Well, we haven't figured that one out yet. We spoke with Robin about it last night for a long time to figure out why, and we think the most plausible explanation is that the smoke gas drops close to the ground, and the radiation meter is near the ground as well, and as it gets closer, the radiation level rises on the meter. We think that's what happens. The same as when you get to a ventilation-controlled fire where the smoke gas is low as well. So in our view, we can't say yet that because of the offensive deployment from outside, conditions improved greatly for the victims, although the temperature did drop considerably. So deployment in fire rooms works. You don't need fancy new equipment. It does work. Attack from outside fire room. That's important because that's not the way we work. We still say we want to get in, so we look for the fire, and then we try to cool the fire gas. It would probably be better to explore the outside surroundings a bit more to seek out the fire. So those are the superficial conclusions we reached. If you look at deployment in the adjacent room, so attack from adjacent room, then the baseline measurement shows something entirely different. So we're at in the fire room, the temperature remained fairly constant. We see that the temperature, when you have 2 spaces, at first the temperature drops and then rises slowly again. that surprised us as well. First, we didn't really understand why it doesn't happen in one room, but it does happen if you have two rooms. We need to analyze that, and we'll use sophisticated techniques for that. I'll get back to that in a moment. If you examine the effect of the various techniques, then you see that most techniques do almost exactly the same. The purple line is the baseline measurement. And if you don't consider the baseline, you think that all techniques work except for ventilation. But we already understood that, because if you open the doors and don't work on the fire, then of course the fire increases. But the temperatures drop here, with the baseline measurement, the temperature was dropping anyway. And the only techniques where that we saw that the temperature kept dropping were air pressure foam and low pressure. So with the other techniques, we're not achieving a significantly greater drop in temperature. So we haven't figured out all the answers yet, but this is interesting news that I wanted to share with you at this point. And this is just about temperature. We also need to consider radiation and other factors, especially what happens with the knockdown. And you see that most techniques manage to extinguish the blaze and the flames, but with some techniques, you see that during the attack, the flames are ablaze again. So the knockdown is not permanent. And that's something else new that we don't entirely understand yet. With all techniques, you get some knockdown, but not with most techniques. Only with low pressure and air pressure foam, in this situation again, we're able to perpetuate that knockdown during the attack. That's the other question. Suppose I have a knockdown and I pull the door open. That's the next sheet. So at the first techniques, we didn't achieve knockdown. At least we didn't observe that. Or rather, during the attack, we saw a reignition, so it wasn't a permanent knockdown. You don't need to consider ventilation because you'll never get a knockdown there. But these two techniques, air pressure foam and low pressure, did achieve that. And some of it was permanent, some of it wasn't. So with low pressure, you see it's permanent, but with air pressure foam, it was only permanent in one of the two instances. So you don't have reignition very quickly, so you have some time to enter, even if you deployed from the adjacent room. And if we try to express this in instructions for you, then you know what distance you have to travel to get to the fire. You don't want that distance to be too great. Is everybody still with me? Okay. And you see how long it takes here with these two techniques. These were the only two techniques that yielded permanent knockdown. You saw that you had 2 to 4 minutes to reach the fire and extinguish it under these conditions. Well, these are some things that surprise us and seem to be more complex than we originally thought. That's why you're conducting these experiments, and that's our mission with our team of experts from the different regions. We want to work with them to see what we're going to make of this. If you look at survival rates, this might be a bit complex, but it's basically the best we could do to simplify it at a glance. Victim 3 is closest to the fire. Victim 2 was between rooms 1 and 2, and victim 1 was in the adjacent room. At the baseline measurement, you see that the temperature was not the problem, not for any of the 3 victims. But the carbon monoxide and the radiation were the biggest problems. That matters. So I think we should shift our focus away from the temperature and examine the other parameters. If you take a look, it's not surprising that none of the techniques yields improvement because the victims were not dying from heat. In all 3 victims were not only the one in the fire room, all 3 victims were succumbing to the other 2 factors. So with the different techniques, you don't see a lot of change in the color of the victims. So we're a bit disappointed because we have not really significantly improved survival rates. Well, I said that the radiation was truly remarkable. This is OB5. Can I have another 5 minutes, please? Because I had a video, but the video didn't really work. I'll accelerate it a bit because it would be interesting to show how this worked at OB5. That was the first time when we invited people from all over the country to observe. We conducted a debate and some discussion. And this was a fun event. It was a fire where a lot of people attended, and they even viewed it from online screens. This was the type of screen in our test setup.
Ik loop dan vast even vooruit op de rest van de presentatie omwille van de tijd.
I'm going to continue with the rest of the presentation to save time, but at OB5, we discovered that exploring the outside setting was extremely important. You should do that with cameras too. And the question is if you can use heat image sensors to show where the fire is. And we did that. So around this building, you see all kinds of setups of heat image sensors to see what we could perceive from outside with heat image sensors. The example is the cold cutter. That's a nice one. You see that the fire is lit. This is the heat image when it's being lit. And now you see the attack. And our counterparts from Amsterdam, who are great at operating the cold cutter, we had them do this. And you can see what the equipment does deep into the premises. You see all these lines. And with a single cold cutter in this building, with that fire load, we got it below 150 degrees within a few seconds. We had about 300 bars, 60 liters per minute in our fire, but the impulse and the strength of that spray reached the back of the building. So that got close to the fire with the thermic load and the turbulence, so that the temperature throughout the area dropped below 150 degrees pretty quickly. And we saw that with all the techniques. So that's the indication. If you don't know exactly where the fire is and it's a large building, then use a technique that has a large radius. Okay, open the door. These results have not been fully analyzed, so I can just give you a general impression. It's fairly dry here. Let's scroll through and see the results for OB5. Okay, let's get back to the presentation here. Here we are. Okay, may I continue? Yes, I can take it from here. This is the setup, and the fire load is in the middle. Now, what you see is that the techniques using the large thrust distances get the temperature below 150 pretty quickly, and then you can get in and extinguish the rest of the fire. Now, the spray nozzle and the fog nail don't have a very long thrust, so they do have an effect, but they don't reach the fire. So this is an interesting one. We still need to analyze this some more, especially the radiation, because we saw the radiation soar from 5 kilowatts per square meters to 25 kilowatts per square meter in some cases. And what you see here is that the victim would succumb in different ways if we did nothing, and if we do something, we're not really changing an awful lot in the survival rate. Now, at a glance, what does the OB yield? Attack the fire room, explore the outside surroundings. That's what I urge you to do. Take a bit more time for that exploration. Use your heat sensor cameras and attack where the fire is. Often you don't even need to go inside. And if the fire is not in the room immediately behind your attack. Then it depends how far away it is, how large the room is. We still need to zero in on that. We'll consult our experts, and the jury's still out on that. But what we are doing now is that story about the baseline measurements. That's a new practice. You see how we're linking experiments and practice with modeling, and that's inverse engineering. What we're basically doing is we're using the results to rework the models to see exactly what the fire did. I see some of you nodding. It seems familiar to you, but this is news to us, and we hope that the combination of those two will teach us a lot about the fire behavior, the fire dynamics. I'm going to end here. I had a short video about the heat sensor cameras. Would you give me time for that, Mr. Chairman? Well, answer is inaudible. Okay, there's no OB6. It's a very short video about heat image sensors that we positioned around the building, and they're used a lot. They're in the same setup as OB5. These are the Argus 320 heat sensor cameras. They have a search and overhaul mode. That's important. You can clearly see the difference between time 0, when you don't see anything, and 15 minutes later. Everywhere in the building, you can see exactly where that fire is blazing. And that's our conclusion, that you can use heat image sensors to discover the fire. There's some pitfalls. You need to know exactly what you're doing, and you need to act quickly. So if you show up after 15 minutes, there's no more difference because the entire building is heated up. And these are the people we deployed. This video is from a bit after the fire, but you can see that in the back of the building it's hotter than at the front of the building. So that tells you why you need to attack from the back of the building, not at the front, because your chances of success are better if you do that. Well, I wanted to show you that video, and I'm glad that the chairman allowed me. Okay. We'll allow 2 questions from the audience. Microphone, please. There it is.
Good. Thank you. So.
You present effectively the effect of the different systems as the objective of water temperature reductions. We know, all of us, we know the properties of the water, also as a water curtain. Did you make any comparison about the efficiency of the use of the water by the different systems, quantity of water that has been used for all the systems?
Yes, we measured the quantity of water that we use in every experiment. I didn't show the results, but we know now that that there is a big difference in water use, especially if you, for example, if you use it for 10 minutes. Of course, you can even calculate 10 minutes low pressure or 10 minutes cold cutter, 60 liters per minute. Then you know how much water is in, and we measured it. So, and then you can see that if you look at just the effect on temperature, it might be the same. But if you look at the use of water, then like efficiency, then per liter of water, there is a big difference.
Nog één of ja.
One more, Ruud. Ricardo, you showed boundary values for survival rates, but most of those values are time-based, so they're doses, so boundary value times time multiplied by time. Have you considered examining that too? Or do those boundary values apply for the same time frame in all cases? Yes, there are 2 types of boundary values. One is for escape. You use the formulas with all the concentrations, and those are time dependent. But if you're talking about survival rates, then we found pretty firm data in the literature. So 8,000 ppm of carbon monoxide will kill you, according to the literature, as will radiation of 6 kilowatts. So those are the values that we set. For example, if you examine radiation. So 6 kilowatts per square meter of radiation is fatal, but what if your measurement shows you that the radiation very briefly exceeds 6 kilowatts per square meter and then immediately drops? Will that kill you as well? According to the literature, it will kill you. It doesn't matter about the duration, and it would almost be an independent investigation to check that out. Did I say that correctly? You conducted a whole study based on the Zutphen experiments. I'll elaborate. You'll be here this afternoon with a smoke detector that it relates to the dose as well as your personal conditions. So an 80-year-old with poor lungs will react differently than a child or an adult. So yes, the thresholds do vary in the literature, especially concerning carbon monoxide. And dose and personal circumstances are factors, so we can't definitely say this person will die. All we can say is the threshold has been exceeded. In the smoke detector presentation this afternoon, you'll see we talk about 80% and 10% survival rates, so those are all statistics. It's not that cut and dry, so you need to make some choices. These were the